Dr. Suresh Ramaiah, he has discussed the analysis of variance in his lecture, testing of hypothesis. But I will discuss the same topic with a low pace, so that you can understand the idea. And my aim is, I have not taken any real data set. I have taken hypothetical data sets, so that you can understand the concept. Because once you understand the concept, once you understand the mathematical idea behind that, programming will not be very difficult. So first I will share my PPT with all of you. Is it visible?
Yes, sir, it is.
Okay, thank you.
Oops.
So uh, outline of my talk is I will introduce the concept of analysis of variance, and then I will focus upon one-way analysis of variance and two-way analysis of variance. In two-way analysis of variance, there are three things. One, we will see how to perform two-way analysis of variance without interaction, and if your null hypothesis is rejected, how to perform post hoc analysis. And we will also see how to perform two-way analysis of variance with interaction. So first thing is, what is analysis of variance? All of you have seen that there is a t-test. In t-test, you compare, if you have two populations, you compare means of two populations. Now, if we want to test means of more than two populations, then how to perform that? So we will actually investigate the problem of deciding whether the observed differences between more than two sample means are purely random, or whether there are actually real differences between the sample means. What do we mean by random and real difference? See, variations may be because of randomness, and variations may be because of some factor influencing the means. So we want to verify whether it is because of random chance, or there is a factor influencing those things. So for that, we use the analysis of variance test to determine if the difference exists between the means of more than two populations under independent sampling. That means the populations which we are considering, they are independent. That is the assumption. The ANOVA, in short, we call analysis of variance. We call it ANOVA. So ANOVA test is actually a generalization of two sample t-test with equal but unknown variances. So I start with very simple example, pulse rate examples. The health of employee working in three different departments of a company is being compared. The resulting pulse rates are given below. That means we are focusing upon pulse rate, and with the help of pulse rates, we are deciding about the health of the employees. So there are three departments in a company: sales department, accounts department, and admin department. So in sales department, we have taken eight, eight employees, and their pulse rates are given here: 72, 81, 96, and so on. In accounts, we have four. Their pulse rates are also given. In admin, we have five. So now our question is extremely simple. We want to test the hypothesis, the null hypothesis, that mean pulse rates of employees are same for all the departments, against the alternate hypothesis that mean pulse rates of employees are different for at least two departments that we want to test. Why this question arises, you may be knowing that if you are working on sales, then there may be a pressure in comparison to admin or in comparison to accounts. So if there is a pressure, there may some increase in the pulse rate. If it is the case, we want to test that. Okay, so basically we want to test the average pulse rate of sales and average pulse rates of accounts and admin, whether all three are same or at least two of them are different. That we want to test. Okay, now what are the assumptions before testing these things? ANOVA test we can use for testing k populations. Here, in this example, we are having only 3 populations, but we can test it for more than 2 populations. That means 3, 4, or 5, and so on. Under the following assumptions, what are those assumptions? The populations are normally distributed. That means we assume the data is coming from different populations, and those populations, the characteristic in which we are interested, that follows a normal distribution. And the second assumption is the population variances are unknown, but we assume that they are equal. That means population variances of first population, second population, and third population, they are equal. And the third is samples are selected independently. Okay, independently within the population and between the population also. So these 3 assumptions are there, and now you must be knowing how to test these assumptions. For example, normality, you know that there is a test, Shapiro will test. You can apply that test to see the normality, or you can plot, box plot. With the help of box plot, you can easily see or at least guess whether your data is coming from normal or not. So I am not going to verify the assumptions. That I assume that it has been covered in the workshop. So my focus is what is the rationale behind analysis of variance. That means whatever is the idea behind that. So the ANOVA approach for testing a null hypothesis H naught concerning multiple parameters is based on deriving 2 estimators of the common variance sigma square. See, we have assumed that all the populations are having common variance. So if I call it common variance by sigma square, so there is something which is unknown to us, which is the common variance. So what we are going to do, we are going to find 2 estimators. That means 2 formula based upon the data which will estimate sigma square. So that means we will have 2 estimators of the sigma square. This is the rationale. And the first one is a valid estimator of sigma square, whether the null hypothesis is true or not. That means first formula which you are using to estimate the sigma square, whether all the 3 populations are having the same mean or not, that formula will not be affected. That will easily estimate the sigma square without any problem. And the second one is a valid estimator only when H naught is true. That means if your null hypothesis is not true, second estimator may not be a good estimator. That may be overestimate or underestimate the null hypothesis. But in this case, it is actually, in addition, when H naught is not true, the later estimator will overestimate the sigma square. Okay, so now you can easily understand we have 2 things. One estimator will always work. Second estimator will work in a good manner if your null hypothesis is true, and if your null hypothesis is not true, it will overestimate. So if you take the ratio of the second estimator to the first estimator, that means above numerator is the second estimator, denominator is the first estimator, and if you take the ratio, and now you can easily understand if your null hypothesis is not true, the numerator will be bigger than the denominator. That means this ratio will be bigger than 1. So now our question arises only simple. If it is sufficiently bigger than 1, that will indicate that our null hypothesis is not true. So the idea behind it, we will reject the null hypothesis when the ratio of the second estimator to the first is sufficiently large. And this is the basic rationale behind the analysis of variance. Okay, that's why, because we are focusing upon estimators of the variance, the name comes the analysis of variance, because actually we are analyzing the variance, and based upon analysis of the variance, we are deciding about the mean. Okay, what technique we use? The technique of ANOVA consists of separating the total variability into components associated with different sources of that variability. These components are then compared, and this enables us to test the null hypothesis that the no difference exists between the population treatment means. What do we mean by treatment means? See, in the example of sales, accounts, and admin, Sales, we are considering one kind of thing. That means if a person has given a job in sales department, so we are treating them that they are the sales employees. So treatment in that sense. Okay. Despite its name, analysis of variance is actually testing the means are same or not. So a one-way ANOVA. Now there are one-way analysis of variance and two-way analysis of variance. So what we do in one-way ANOVA, a one-way ANOVA test compares population means based on one categorical variable. We call it technically a factor. For example, type of the employee. So employee may be from the sales department, employee may be from admin department, or it may be from account department. So this is a factor, and this factor has three levels: sales, accounts, and admin. So you have only one factor, the category in which your employee belongs, and it has three levels: accounts, admin, and sales. So for instance, this I have already discussed. So in one way ANOVA, if we see the mathematical setup, we will have in general K treatments. K treatments means there are K kind of populations in which you are interested, and each population will give you NI responses. Okay, and total available data will be, of course, summation of Ni, that means N1 plus N2 plus up to Nk. That means if there are three treatments, then number of data or response variable coming from first treatment, second treatment, third, if you add them, that will be the total data. And mathematically, we define Yij. This is the response. So Yij means it is the jth observation using treatment I. Okay. For example, sales. If you focus upon this, you can easily see there are three things: sales, accounts, and admin. So our K is 3. In sales, we have 8 observations. So our N1 is 8. In accounts, we have 4 observations. So our N2 is 4. In admin, we have 5 observations. So our N3 is 5. And in total, we have 8 plus 4 plus 5. That means 17 observations. So you may be thinking that why I am doing all these small things. See, once you understand the idea, the complicated problems can be solved. Okay, so that's why I have taken very simple toy example. Okay, so now from here, what we say, if I call it Y12. So Y12 means you are focusing upon first treatment, that means sales, and out of that second observation, that means 81. So Y12 actually stands for 81. Similarly, if I focus upon Y31, so Y31 will be the third, that means admin, and the first observation 61. Now what happens, we can find the average of pulse rates from the sales department. That means average of 72, 81, 96, 75, 69, 88, 74, 102. So if I find the mean, so this is called treatment mean. We denote it by M1 bar, and it comes out to be, in this case, 82.13. Similarly, you can find the treatment mean for accounts, that comes out to be 70.5, and admin, that comes out to be 69.2. And if I assume that all these three, sales, accounts, and admin, there is no difference, they are coming from the same population, that means their means are same, then we can find the overall mean. Overall mean means considering all 17 observations. So if you consider all 17 observations coming from single population, you can find the overall mean. So the overall mean is here 75.59. Now see the idea. What we want to compare, whether means are same or not. So if I assume that mean of the sales department is 82, mean of the account department is 82, mean of the admin is 82, then you can easily guess and easily understand that overall mean will be 82. So if means will be same, the individual mean will be very close to overall mean. Here you can see M1 bar, which is 82.13, and M bar, that means overall 75.59. There is a difference between them. There is a difference between 70.5 and 75.59. There is a difference between 69.2 and 75.59. Now, question arises, these differences between individual mean and the overall mean, whether these differences are by chance or there is some reason behind that. Okay, here, since you have assumed that there is a normal distribution, so if you are seeing the differences 72, 81, 96, so there is a variation row wise. There is a row wise variation. So that row wise variation is actually explained by sigma square, because we are assuming the data is coming from normal distribution with variance sigma square. Second, in accounts similarly, that means the variation in the second row, that is also we are assuming that it is coming from some normal distribution with variance which is unknown, but it is sigma square. So this variation is also governed by sigma square. The variation in the third row is also governed by the sigma square. But variation in the columns of means, whether that is also governed by sigma square or it is because of there is a different population, sales, account, and admin. So you can easily understand this with the help of a graph. So before going into graph, we want to discuss about why we cannot use t-test here. That means we are going to discuss why analysis of variance is important. So now we want to see if there is a significant difference between the mean pulse rates for three departments. So we can compare that mu1 is equals to mu2 is equals to mu3. That means mean of the first population, mean of the second population, and mean of the third populations are same. And what will be the alternate? Alternate, of course, two of them are different. Now, one may wonder whether we can use t-test or not. That means, can we use t-test three times? That means first we compare mu1 and mu2, then we compare mu2 and mu3, then we compare mu3 and mu1. So instead of comparing mu1 is equals to mu2 is equals to mu3, that means the equality of three means, can we use t-test and we compare equality of two means with all possible pairs, mu1, mu2, mu2, mu3, mu3, mu4. So I am going to show you that if you go by second, that means by t-test, by pairwise comparison, there will be some problem. Okay, I am going to discuss that. So, however, this is not best solution. Why this is not best solution, that we are going to consider with the help of type 1 error. So you recall that type 1 error commits if you reject your null hypothesis when it is true. That we know is the type 1 error. So if you focus upon probability of type 1 error, that will be the probability of rejecting H0 when the null hypothesis is true. And of course, it will be same as 1 minus probability of do not reject H0 when H0 is true. Now, if we assume we wish to test the equality of three means using pairwise comparison. Okay. So when you do that, in each test, you will fix alpha. Okay. Because there are three tests, you have to fix alpha. So there are three possible pairs. And for individual test, if I want to find probability of do not reject H0 when H0 is true, so that will be 1 minus alpha. If I fix alpha as 5%, this will be 0.95. So in a particular test, probability of not rejecting H0 when it is true, or you can say that probability of correctly accepting the null hypothesis if it is true is 0.95. So for three tests, if you are perform them independently, it will be 0.95 to the power 3. That means 0.86. Okay. Now if you find probability of type 1 error, that will be 1 minus 0.86, that will be 0.14. Now you can see each t-test has maximum error 5%. Now if you perform three t-tests, For the comparison of mu1 is equals to mu2 is equals to mu3 pairwise, your error will increase from 5% to 14%. So pairwise comparison is not good because it inflates the error. That's why we do not use t-test. So we will go for the analysis of variance, which actually allow us to compare all three populations mean, equality of all three population means simultaneously. Okay. Now you can see if three population means are equal, which I was saying you, if three population means are equal, then M1 bar, M2 bar, and M3 bar, that means sample means, what you are getting from the data, they will be close enough. We can see from the graph. In this graph, if all the data, that means you have three populations, and all three populations, they are having same mean, they are having same variance, then from first population, if you get M1 bar, from second population, you get M2 bar, and from third population, you are getting M3 bar. And the true mean is mu. And this is the variation. So you can understand the variation between M1 bar, M2 bar, and M3 bar. That variation is because of sigma square. Okay, that means variation within a within a population is due to sigma square, and variance between the population is also due to sigma square, because mu mean is same, all the three populations coincide, and these variation will be governed by sigma square. That means the variation of the common population, common distribution. Okay, this is the left hand side graph. Now if all three populations are different, for example, on the right hand side graph, you can see there are three populations. First one having mean mu1, second one having mean mu2, third one having mean mu3, and variances are same. Okay, but means are different. Now from the first population, you collect the data, find out the sample mean, you may get M1 bar. From the second population, that is the blue one, you select a sample and find the sample mean, you may get M2 bar, and from the third, you can get M3 bar. Now you can easily see the difference between M1 bar and M3 bar, the rightmost and leftmost. The difference between M1 bar and M3 bar, that is not by chance. That is because mu1 is far away from mu3. That is because of that. Because mu1 is far away from mu3, so M1 bar is far away from M3. So if I find the overall mean, the difference of M1 bar from overall mean and the difference of M3 bar from overall mean, that will be different. That will be significant. So this is the idea. So in first, the variation is governed by sigma square, but in second, variation is not governed by sigma square. It is governed by two things, sigma square as well as the different means. Because there are different means, so variation is also for that cause also. Okay, so this is the graphical representation what happens in analysis of variance. So I have explained these things. Now with the help of this, we can make a statistical model. So Yij is your response. That means in our example, pulse rate. So there will be common pulse rate, mu. That means there is a standard pulse rate. Now, if you are working in sales department, you will have some variation because of sales, because of your pressure which you are feeling in sales department, working in the sales department. That we are representing by tau I. Tau 1 for sales, tau 2 for accounts, tau 3 for admin. And then there will be some random fluctuation because the data is coming from some distribution. So that random fluctuation I am denoting by Eij. So there are three things. Mu means there will be some pulse rate, plus there will be some effect of sales department, plus there will be some variation because individual person to individual person. Now these errors are, we assume that they are normal sigma square. So in simple manner, you can say that your response is a constant plus effect of the treatment plus some error. And if you combine all these things, the distribution of Yij will be normal, mean with mean mu plus tau I plus sigma square. Now, if tau I becomes 0, then all the three or all the k treatments will have same distribution. So we want to find out whether tau i's are 0 or not, or you can say whether mean is mu plus tau I, we call it mu I. So our hypothesis is mu1 is equals to mu2 is equals to mu k. This can be converted into this equivalent hypothesis, which is tau1 is equals to tau2 is equals to tau k is equals to 0. That means there is no effect of the treatment. And the alternate hypothesis that at least two of them are different. Remember that I am saying at least two of them are different. I am not saying that all of them are different. At least two. So what we do actually, if you recall, I have said that we will focus upon two estimators of sigma square. Okay. One estimator will always work. One estimator will work efficiently if your null hypothesis is true. Otherwise, it will overestimate. Now we are going to see how to find those two estimators. So the total variability, we are actually partitioning into two components. One measuring the inherent variability. Inherent means which is because of distribution, and the other measuring the variability between the treatments. That means the impact of sales, accounts, and admin. So total variability, we call it SST, that can be partitioned into SSE and SSB. SSE, that means inherent variability, we call it error sum of a square or sum of a square due to errors. Errors means this is inherent. And SSB, sum of a square due to treatment or between sum of a square. That means between three populations. For example, here you can see first one, total variability. How to find total variability? There are observations Yij. There is overall mean M bar. You find the difference between the observations and overall mean, take the square and add them. So this will be the total variability. Now you focus upon Yij, for example, first row. From the first row, each element you subtract M1 bar. So that will, and take the square and add them. So that will give you the variability due to sales. Then you do the same thing for accounts, same thing for admin. So that will be first part, which is because of error, because this variability will be there, row variability will always be there. And the second one is, you can see mi bar minus m bar. That means the difference between individual population mean and the overall population mean, and you are taking the square, multiplying by ni, because ni components are there. So each component there will be weightage kind of thing. So this second part is known as SSB. This is a mathematical formula. This can be proved. So we have separated these variabilities. Now you can easily understand the second one. If in original populations mu1, mu2, mu3 are far away, you can easily understand that m1, m2, and m3 will be far away from m bar. So this second term will be bigger if mu1, mu2, mu3 are different, or at least two of them are different. So it will be bigger. So we are actually focusing upon second and first. So what is there? So I have explained all these things actually. Now we focus upon first estimator, and the first estimator is SSB divided by K minus 1, because we had K treatments. So we are dividing it by K minus 1 just to average out the things. So your first estimator is SSB upon K minus 1, and it will estimate sigma square. And mathematically, it has been proved that SSB upon K minus 1 will tend to be larger than sigma square when H0 is not true. That means it will overestimate the sigma square. Okay. And the SSE upon N minus K, that will always work as a good estimator of sigma square, whether H naught is true or not. So this ratio, we call it between treatment mean square divided by error mean square, because when we are divided by k minus 1 and n minus k, these are called mean squares. So this test statistic, when this test statistic will be sufficiently large, that will indicate that SSB upon k minus 1 is overestimating sigma square. That means H naught is not true. Okay, so we say that reject H naught if this test statistic SSB upon k minus 1, SSE upon k minus 1 ratio of this is greater than or equal to some critical value. So this actually follows F distribution, and this is critical value of F distribution with degrees of freedom k minus 1 and n minus k. Now from here you can easily see that ANOVA is only one-tailed. This is on the right hand side. You are rejecting your null hypothesis if your test statistics is bigger than some critical value. That means you are on the right hand side, right tail. So this, remember that analysis of variance is right tail test. Okay, because you have to mention this in the R, and do not reject it otherwise. So in summary, what I am saying, if all the means are same, we have two estimators, both will work fine. If H naught is not true, the estimator which I have put on the numerator, that will overestimate, so ratio will be bigger. So if ratio is sufficiently large, your null hypothesis must be rejected. That is the idea behind it. Okay, now in writing output, we always write down analysis of variance table. How to write down? We have a source of variation, that means between treatment, then there is a error, then there is a total variation. So between treatment, we call it degrees of freedom, because there were k treatments, so degrees of freedom is k minus 1. There are total n and degrees of freedom n minus 1. So if you subtract total k minus 1 from n minus 1, you will get n minus k. That means error degree of freedom. Then you write down the sum of squares, that means the sum of squares between sum of squares, error sum of square, and total sum of squares. Now if you divide this sum of square by its degree of freedom, that is called mean square. Similarly, SSE upon n minus k, SSE upon n minus k, this is mean sum of square due to error. So these are the two estimators. Now you take the ratio of these two estimators, which is MSB upon MSE. So this will be your test statistic. If it is larger than the critical value, you reject the null hypothesis, otherwise not. So this is the final output. We always write down, when we perform analysis of variance, we write down the output in this manner. This is the actually this is the SPSS output. I will show you in R also. This is the SPSS output. You can see between groups, sum of square is this. Within group, this is this. Now you can see this is 649. This is 1336. Degrees of freedom, mean square, F, significant. So this significant is actually the p value. So this p value is 0.063. So you know that if your p value is, if I fix alpha as 5%, so my p value is bigger than, so my p value is is more than 5%. So we are not going to reject the null hypothesis. If your p value is less than alpha, you reject the null hypothesis. So with the help of p value, we are not going to reject the null hypothesis. If you focus upon critical value is 3.74 and observed value is 3.4. Of course, your observed value is not bigger than 3.74 because your observed value is not crossing the critical value. So the conclusion will be same. We cannot reject the null hypothesis. That means in this example, we cannot say that mean pulse rate are different for these three populations. We cannot conclude that. Okay, now we are going to see the same thing in R, how to perform this in R. So this is a file of R markdown. Someone will, I think, discuss R markdown tomorrow. So I have focused upon direct calculations. Direct calculations means I have actually included three methods. One method is direct calculation. That means you don't know you don't know any package, anything. Then how to perform one-way analysis of variance. So in that, if you focus upon first line, what I have created a sales a vector, and it contains, you can see it contains, yeah, what happened? Yeah, it contains the data, pulse rate data of sales employees 72, 81, 96. That was the this is first line. In second, I create the data of sales account department. In third, I have created data of admin. Then I have combined all three data. Pulse dot rates, I have combined sales, accounts, and admin data. Okay. Then I have just seen what is the length of sales. That means what is N1, what is N2, what is N3, and then N, which is N1 plus N2 plus N3. Then I have taken a print of N1, N2, N3. So if I run this chunk, if I run this, why this is not running? So I'm running this. Now you can see here, first it has created a vector of accounts, then admin, and all these things. So it has printed everything here. See, these are the outputs. I will show you these things here also. It will be more easy to show you. Is it visible?
Yes, sir.
It is.
Is also visible. So I'm showing you on the this. So these are the direct calculations. So I have entered sales, accounts, admin. Then I have made pulse rate data. Then I have seen what is N1, what is N2, what is N3, and what is total. So you can see N1 comes out to be 8, N2 comes out to be 4, N3 comes out to be 5, and 17. Then I have found mean of sales. That means M1 bar. I am not writing M bar here in R. So these are the R commands which you are seeing in gray box, and these are the outputs which you are seeing in the white boxes. Okay. So I will send this file to all of you. You can enjoy by running all these things. I am not going to waste time on running these commands. So M1 is equals to mean sales, M2 is equals to mean of accounts, M3 is equals to mean of admin. See, what I am doing, I am just writing everything from the scratch. That means I do not know anything in R. So how to write down all the things with my simple commands. Find out the mean of pulse rates and print M1, M2, M3, and M. Now you can see mean comes out to be 82.125, 70, 69, 75. This is the overall mean. 75 is the overall. Okay. Now I am going to find out the between sum of squares. So if you remember the formula, if you remember this second one was between sum of square. That means summation I from 1 to 3 ni mi bar minus m bar whole square. This was the between sum of square. So I am finding this between sum of square. Here SSB is equals to n1 star m1 minus m whole square. You can see n1 star m1 minus m whole square plus n2 star m2 minus m whole square plus n3 star m3 minus m whole square. So I am getting SSB. I am taking the print of SSB. This comes out to be 649.4426. Okay, which you can see there. Now we are focusing upon MSB, which is SSB divided by K minus 1. K minus 1 means number of treatments are 3 minus 1. That means SSB divided by 2. So if you find out MS 4.7213, I can show you. I have included the SPSS output. Now you can see here, this is 324.721 and this is your R output. 324.7213 and this is the SPSS output. Both are same. Now you focus upon SSE. Now SSE, I have written a formula here. I will show you why I have written this formula. This is your SSE. This is your SSE. This summation I from 1 to 3, j from 1 to ni, phi ij minus mi bar whole square. This is your SSE. Now, if you focus upon only this part, summation j from 1 to ni, yij minus mi bar square. If you divide this part by ni minus 1, you know that it will give you the sample variance. If you remember the formula xi minus x bar whole square, if you take the sum and divide it by 1 upon n minus 1, you will get the sample variance. Okay. So if I divide this quantity by ni minus 1, because there are ni observations. So if I divide it by ni minus 1, I will get sample variance for the sales department, accounts department and admin department separately. So that's I am doing in our programming. I am writing here n1 minus 1, see, n1 minus 1 multiply by variance of sales plus n2 minus 1 multiplying by variance of accounts plus n3 minus 1 multiply by variance of admin, and I will get SSE, which comes out to be 1336.675. And if you divide it by n minus 3, that means 17 minus 3, you will get MSE, which is actually 95.47679. You can see this output. You can match this output here. See, 95.4777. That is also here. 95.4777. So after finding out these things, we know that how to find your test statistic. You know, test statistic is the ratio of two estimators. First estimator is MSB and second estimator is MSE. You find the ratio, that is the test statistic, that means the observed value of test statistic. So observed value comes out to be 3.4015. Now this is the observed value. Now you want to find what is the critical value. The same you can get here. This is the observed value, 3.401. This is the observed. What is the critical value? Here it is written as 3.74. You can see the critical value is written as 3.74. So how to find critical value here? In R, see, critical value means your test statistics is bigger than something, and bigger than what? So bigger than if I find out the p value. So test statistic p is bigger than the observed value. That means you are finding the PF for f dot observe degrees of freedom. That means you are finding the value of the F distribution at point this degrees of freedom 3 minus 1 n minus 3. Now you can see that I have written lower tail is false. Why lower tail is false? Because it is only right tailed. Because bigger than, I need only bigger than. So lower tail is false. So it is actually coming to be this, and this is the p-value. So this is the formula for finding the p-value. P-value comes out to be 0.06, which I have shown you here also, 0.063 almost. So if p-value is bigger than 5%, we are not going to reject a null hypothesis. If, for example, I want to find the critical value, so I will find the quantile at 5% with the same degrees of freedom. Lower tail is again false. So this is the critical value, 3.74 approximated. So this is the R. These are the R commands if you want to find uh, if you want to perform one-way analysis of variance without using any package, anything, any inbuilt formula. I have just written everything here. Now, but there are, of course, there are packages and formula by which you can perform this directly. So for that, we are going to do this. What we are going to do actually, we are now creating two different variables. One contains the pulse rates, another contains the population name from which these pulse rates are coming. That means whether it is sales or whether it is from accounts or whether it is from admin. So for that, I am using the command function stack. All of you must be knowing the stack. So it will create two columns, and inside I am taking the list of all these three. That means sales have been given name sales, accounts data have given name accounts, and admin data have given name admin. Now if you focus upon pulse.data, it will contain two variables. I have written names pulse.data. If you run this command, it will give you names of the variables. These are values and ind. So how data looks like? If you run pulse.data, our data looks like this. See, these are the 17 observations in first column. In second column, you are getting values. That means the observations. In third column, you are getting from which this observation is coming. 72 is coming from sales department. 81 is coming from sales department. 96 is coming from sales department. So I have written that. So I have created a data frame kind of thing. Now I have a data frame. Now with the help of this data frame, we will perform analysis of variance. And the simple command is one-way.test. One-way.test. Inside, you have to write down your model. So what is our model? We want to find values which are depending upon independent variables. So values, this is our model. Okay. And what is data? Data is equals to pulse.data. Whether you are assuming variances are equal, of course, since I am performing the analysis of variance, we are assuming that all three populations have same variance. So with these things, if you enter it in R, this will be the output. One-way analysis of means it will give you two things. Data, we have values and int. F is 3.4011, that means the observed value. Numerator degrees of freedom is 2, denominator degrees of freedom is 14, and p value is this. So it only gives you only this much. You are not getting what is MSC, what is MSB, you are not getting those things. It only gives you p value, f observed, numerator and denominator degrees of freedom. But you can conclude that p value is bigger than 5%, so we are not going to reject the null hypothesis. So this was the second method. Now there is a third method. There is a third method, the function AOV, analysis of variance. The function AOV, analysis of variance. So in that also we write down our formulation, that means values tilde ind, and our data. Data is pulse.data. So I am performing analysis of variance on this model with this data, and putting all these things in RES. Now, if you write down RES, this will print the output. This will print the output. And this AOV function gives you the summary just like analysis of variance table. So it is actually give you the summary in the form of table. So you can see the formula call is AOV. That was the formula call. What are the terms? Terms are sum of squares it is giving you. First one, second one. See, it is using the name residual. Residual stands for error sum of square in our slide. And these are the degrees of freedom. And this is the standard error of the residual. This is nothing but 1336.6750 divided by 14. Nothing there. So if you write down summary .res, it will exactly provide you the analysis of variance table. You can see here, analysis of variance table. We have IND, we have residuals. It is not going to give you total degrees of freedom 214. That means it is actually giving you this table without the last row. Without the last row. Last row it is not giving you. It is giving you this table, if you can see. 2, 14, this number, and all these things. So it is giving you F value, that means the observed value. It is giving you the P value. And you can see there is no star or double star in this P value. If you get triple star, that means your P value is almost 0. If you get double star, that means your P value is approximately 0.001. If you are getting single star, it is this. If you are getting dot, this is this one. That means this is actually giving you the significance level at a different alpha. So since we are getting dot, that means it is bigger than 5% and less than 10%. So this was about the one-way analysis of variance. Now we move towards two-way analysis of variance. I hope there is no question up to this point. Okay.
Sir,
Now, yeah.
if you have data in Excel sheet, then you can come import into R and can you do the analysis, sir? Is any comment?
I know. I know that. I know that. I will show you that in two-way analysis of variance. See, what I have done, I have shown you the simplest methods.
Yes,
now I will move to the complicated methods. Okay. So in two-way analysis of variance, I will show you how to perform this with the help of Excel sheet. I will show you that.
Okay, sir. Thank you, sir.
So the one-way ANOVA test basically focus upon one categorical variable. So if you have two categorical variables, now if you have two categorical variables and you want to find the whether there is an impact of two categorical variables on the response variable. Now you can think on the response variable, first categorical variable will have effect, second may have effect, and there may be some interaction effect. Some interaction effect means both are actually interacting with each other. For example, when you read something for 1 hour, that means there is a factor time. And if you read it with a high concentration, that means there is a factor concentration also. So if you read something for some time with some concentration, so there will be an impact of your learning which is due to time, which is due to concentration, and there will be some interaction of the time and concentration. For example, if you are learning something for 1 hour with high concentration, that will have different effect. If you are learning for 1 hour with low concentration, so there is an interaction effect. We are going to focus on that also. So we have two factors. So data looks like this: y11, y12, y1j, y1n. We are considering that this is the data is coming from equal number of observations we are getting. Okay. So our data looks like this. There is a row factor and there is a column factor. We call it row factor and column factor. So, and we are assuming that we are getting single data from a cell. That means y11, only one data from first row and first column. That we are assuming in this, at least in the this simplest model. So what is our model? Our model now becomes Yij is equals to mu. That means there will be some reading outcome, mu plus tau I, impact of time, how much you have read, how much time you have devoted, plus beta j, what was your concentration level, that means impact of concentration, and then there will be Eij, that means the individual person will also have some kind of thing. So these things, this is your model, and in this model we assume that there is no interaction. Okay, and we assume that one observation per treatment combination. So if this is the model, what are the assumptions? Of course, dependent variables should be measured as continuous level. Independent must be 2 or more categorical variables. Okay, and independence of observations must be there. Significance outliers must not be there, and of course, normal distribution must be there, and homogeneity of variances must be there. That means variances are same. Okay. Now, what are the hypotheses? Hypotheses are tau i's are 0 against not all tau i's are 0. That means in first you are saying that there is no treatment effect. In second you are saying that there is some treatment which is affecting. And similarly, I have all beta j 0 against all beta j are not 0. So here we will partition again. So now you can see there will be variability. First, due to inherent variability, there will be some inherent variability, and there will be some variation because of first factor. For example, time. There will be some variation because of the second factor, that is the concentration. So I am dividing total variation into three parts, three components: SSR, that means the variability due to rho factor; SSC, that means the variability due to column factor; and SSE, that means the inherent variability, that is the variability due to error. Okay, so when you divide these three, now you can see SSE, this estimate, if you divide it by degrees of freedom, this will be an estimator of sigma square, and this estimator will always work. SSR divided by its degrees of freedom will have different estimator, and clearly if there is a variability due to rho factor, this SSR divided by its degrees of freedom will overestimate sigma square. Similarly, SSC divided by its degrees of freedom will overestimate sigma square column effect. That means that the column factor has some effect on the response variable. So again, we are going to have estimators of that kind. So see, we are interested in tau y is equals to 0. So what we have done, we have taken our test statistic SSR divided by its degrees of freedom, that means variability due to rho divided by its degrees of freedom, and SSE divided by its degrees of freedom. So denominator will always be related to SSE, because that is not going to change whether your H0 is true or not. That will estimate the sigma square very well. Now this ratio will be significantly large if SSR upon m minus 1 is high, and that will be high if H0 is not true. So similarly, you can reject the null hypothesis if this is significantly large, that means it crosses the critical value. Now in second, you just change the numerator. Now numerator becomes SSC divided by n minus 1. That means between column mean square, and you divide it by error mean square. Now see, we have three estimators now. First estimator is based upon rho factor, second estimator is based upon column factor, third estimator is based upon error. So that third estimator will always estimate sigma square well. First and second may be overestimate sigma square depending upon whether rho factor is significant or not, whether column factor is significant or not. So we are just taking the rho factor variability divided by error, then rho factor variability divided by error, column factor. That means we are comparing the variability with error. Remember that. And if it is large, that means it is bigger than inherent variability, that means there is some impact of the row factor or column factor depending upon which one is large. So in this, this kind of output will be there. Between rows, degrees of freedom, sum of squares. When you divide sum of squares by degrees of freedom, you will get mean squares. Between columns, degrees of freedom, SSC. You divide SSC by degrees of freedom, you will get mean squares. And then error. When you divide mean squares by error, you will get test statistic, first for the row and second for the column. This is the final analysis of variance table. Okay, we will again see a simple example, a hypothetical example, just to understand the idea. So if we have 5 different standardized reading achievement tests and they were administered to each of 6 students, their scores are this. Examination 1, when student 1 has written examination 1, he or she got 75 marks. When student 1 wrote examination 2, he got 78 marks and so on. So these are the marks. Now you can easily understand these output, that means the score, they will depend upon student, which student is writing the exam, and it will also depend upon the quality of examination. That means whether examination contains hard questions or easy questions or average questions, it also depends upon that. So there are 2 factors now. One is examination and other is student. Now you can see there are 6 students, so we can say that factor student has 6 levels, and there are 5 examinations, so we can say that factor examination has 5 levels. So this is two-way analysis of variance example. Now we are going to perform it with the assumption that there is no interaction. So our null hypothesis will be mean score is unaffected by examination. This is one of the null hypothesis. Mean score is unaffected by the student. This is another null hypothesis. Of course, alternate will be mean score is affected by some examination and mean score is affected by some student. Now, before performing this, we see whether there is an interaction between these two or not. So this plot, I will show you all these things in R. First, I'll explain here. So we will plot this plot is called interaction effect plot, interaction plot. So what it shows you actually, you see on the x-axis we have main factor examination. On the y-axis we have scores, and here there are students inside. That means lines, different lines of different colors are representing the students. So 5, 6, 1, 2, 4, 3, these are the students. So the uppermost line represents the 5th student. That means 5th student is getting highest marks in all the examination. Now you can see that means examination is not affecting the 5th student much in terms of the getting highest marks. And then 6th student is the second highest marks he or she is getting. Then there is first student, then there is second student, then there is 4th student, then there is this. That means the pattern is almost same for all the students between examination and marks. For all the students, pattern is same. So you can see that if these lines are almost parallel to each other, we conclude that there is no interaction. Okay, this is the idea. So in this, there is no interaction. We assume that we have shown with the help of this graph. And if you perform analysis of variance two-way with R, this will be the output. How to perform, I will show you. This first I will explain the output, then I will show you the commands. So this is the output. Student, you remember there were 6 students, so degrees of freedom is 5. Examinations, there were 5 examinations, so degrees of freedom is 4. Residuals, that means error. So you have m minus 1 times n minus 1, that means 5 times 4, 40. Sorry, 20. Then these are the sum of squares. These are the mean squares. How you found mean square? Just divide your sum of square by degrees of freedom. Then you are getting F value for the student. That means you are actually taking the ratio of the mean square with residuals for student examination, and then you are getting the p value. So first p value, you can see it is 3.54 into 10 to the power minus 16, very small, almost 0. And the similarly third one is also almost 0. So you can see 3 stars here. So 3 stars indicates that p value is almost 0 and it is highly significant. That means you reject your null hypothesis. And what was your null hypothesis? That means there is no impact of students on the marks. There was no impact of the examination on the marks. No, we can say that there is an impact of a student as well as examination on the marks. That we are actually getting here. We are rejecting it. Okay. Now we will show you this in R. Now again, I am entering the data S1, that means student 1. So I have entered the data of student 1. Student 1 means actually what I am doing, you can see I am entering the data column wise. Student 1 is getting marks 75, 78, 80, 73, 75. So I am entering the data of first student, then second student, then third, then fourth, then fifth, then sixth, and then I have combined all of them. Now I am going to define factors. So factors means first factor is a student. Okay. So how you define? See, this data 75, 78, 80, 73, 75, it is coming from first student. So we attach 1 to all these numbers. We are going to attach 1 to all these numbers. Then we are going to attach 2 to all these numbers. Then we are going to attach 3 to all these numbers. So we are going to define factors, replicate 1 to 6, 5 times. So when you replicate 1 to 6, 5 times, 1 will be replicated 5 times because first student is writing 5 exams. 2 is replicated 5 times, 3 is replicated 5 times, and so on. And these are the first factor I have defined. Now, how you define second factor? See, this data, if you focus upon this data, second factor is examination. Now, see, 75 is actually first exam, 78 is actually second exam, 80 is third exam, 73 is fourth exam, and 75 is the fifth exam. That means it should be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. So I have to define second factor as 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So for that, what I have written, I have defined replicate 1 to 5, 1 times, and then just repeat it 6 times. That is the examination factor. So you can see 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5. So actually you are attaching factors to your data. Then I am going to see the interaction effect or not with the help of interaction plot. So the command is, the function is interaction.plot. Examination is the main factor. Then there is a student. Then you are going to plot a scores, and colors I am using 1 to 6. There are 6 colors. X label is examination, Y label is mean of scores. So after running this, you are going to get this graph, which I have already explained. After this graph, we can say that there is no interaction. So how to perform two-way ANOVA? So now there is, again, I am going to use AUV. AOV means analysis of variance. Now model is scores tilde student plus examination. So we write down plus if there is no interaction. So our model is, that means we are focusing upon additive model. So student plus examination. If you find the summary of these things, you will get the same table which I have shown you in PPT. You will get the same table. Now, from here, we can say that there is an impact, there is a difference in scores due to student there's a difference in scores due to examination. Now question arises, where is the difference? Where is the difference? That means difference is between first and second student, or difference is between first and fifth student. Because analysis of variance only tells you there is a difference. It is not going to tell you where is the difference. So for that, we have to perform post hoc analysis. So remember, post hoc analysis which will only be performed if there is a difference. Because if there is no difference, to find where is difference is actually illogical. So post hoc analysis, there are many tests for post hoc analysis. I have just named two, Bonferroni and 2K-HSD. And then in this lecture, I am just going to focus upon 2K-HSD. So our command is very simple, T capital UKEY capital HSD and 2-way, because you have already stored your data after analysis of 2-way in 2-way. So what 2K-HSD actually gives, it now compares pairwise. Now you can see if there is a pairwise comparison, that may inflate type 1 error if you use t-test. So in this 2K-HSD, they have prepared this test in such a manner that type 1 error will not be inflated. Okay, I am not going into the theory. I am just going to discuss what are the outputs and how to interpret or read the output. So this is the output. 2K multiple comparison of means 95. I have taken the confidence interval. I have fitted this model, and first is the student. That means it is for the student. Now what it gives you actually, it takes all the pairs of the students. You can see it gives all the pairs. 2 1 means 2 students, second and first, 3 1, 4 1, 5 1 and 6 1. That means the difference of the second, third, fourth and fifth and sixth students with the first students, then 3 2, 4 2, 5 2. That means all possible differences, and you focus upon the confidence interval. So if you focus upon first confidence interval, its lower part is negative, its upper part is positive. That means 0 is in between. So if your confidence interval contains 0, you can say that that coefficient is not very significant. That means that difference is not very significant because 0 is there. In 95% confidence interval, 0 is there. So this difference is not significant. But if you see second one, both are negative. That means 0 is outside. So this difference is significant. There is a negative difference which is significant. If you focus upon the third one, again difference is significant, and so on. You can explain. In examination, you can show same thing, but analysis of this output is actually difficult. So we can plot it. With the help of plot, it will be easy to understand. So the command is plot 2K-HSD, lasso is 2. So this is the plot. Now see the first plot. This is 95% family-wise confidence interval for students. Now you can see this vertical dotted line represents 0. This vertical dotted line represents 0. So if your confidence interval is passing this vertical line, those are not significant. Others are significant because all the confidence intervals which are on the right hand side, they indicate significant positive difference. All which are on the left hand side, they indicate significant negative differences. Okay, so you can say that 3 and 1, they are significantly different. 5 and 1, they are significantly different. 3 and 1, 5 and 1. So if you remember this example, see here. 3 is represented by green and 1 is represented by black. From this graph also, you can see green lines are far from black. So there is a significant difference between 3 and 1. You can see there are actually 3 groups. Green is alone, black and all these 2 are alone, and these 2 are alone. So these are the differences which are now showing in these confidence intervals. Similarly, for the confidence interval family wise, so now these are the post hoc analysis. Now we will quickly go through two-way ANOVA with interaction, and here I will use a data set and I will show you how to call it. And the data set I have taken from this website. This data set I have taken from this website, and what this data set contains actually. So you are researching which type of fertilizer and planting density produces the greatest crop yield in a field of experiment. You assign different plots a field of different combinations of fertilizer. There are 3 types of fertilizer, and the planting density 2, 1 is low, 2 is high. And then you measure the final crop yield in bushels per acre at harvest time. Now we are going to use two-way ANOVA. So what is data set? I will show you first the data set. This is the data set. So here density 1 2 1 2. First column represents this plant density, and it contains 2 1 2 1 2 block, fertilizer and yield. So this is the data set. So from here, how you perform this? First you have to read the file. So crop.data is equals to read.csv. It is comma separated file. I have given the path of the file. So first I have given the path. So it has taken the file. See, I have written header is equals to true, because if you see the file, it has header, density, block, fertilizer and yield. It has given the name. So header is true. Then column classes, first factor, factor, factor and numeric. You can see factor, factor, factor and numeric. Why? Because first is density, which is a factor, block is a factor, fertilizer is a factor, yield is the numeric value. After reading the data, it is again very simple. You write down AOV, simple analysis of variance, and write down your model. Now your yield, the model is fertilizer star density. Star you are putting instead of plus sign. So if you are putting plus sign, it will take care additive model. If you are putting a star, it is actually going to see additive as well as interaction. Summary interaction. So this is the interaction. You can see here, this is the output. See, fertilizer density. So this row actually represent the interaction, and you can see p value is not very small. P value is 53%. So you are not going to reject the null hypothesis. And what was the null hypothesis? There is no interaction. So you cannot say that there is an interaction.